Thanks, Pan. Again, my name is Guillermo Baigorria, Guy, and well, I will be presenting this understanding uncertainties of climate models, but in terms of agriculture, okay, in terms of crop, what it means for us as agronomists, okay, the impact of climate models. And I will be talking not only about climate change, okay, but also in terms of weather forecast and also in terms of seasonal climate forecast. Seasonal climate, we are talking about 3 months, 6 months in advance, okay, and what this type of information can be produced by global models, global circulation models or regional circulation models, and how we can link and use this type of information. Well, I have a joint appointment at the School of Natural Resources at the Department of Agronomy and Horticulture, and I guess it's important for you to know a little about my background, because I am a meteorologist, okay, but I did my master's degree in crop physiology, okay, and I did my PhD in soil sciences and land evaluation, okay, so totally completely different things. And then I moved to Florida, to the University of Florida, working in a system approaches, okay, putting all together this climate information, let's see numerical models, let's see ENSO, El Nino signals, let's see observed data from weather stations, etc., together with crop models, empirical models, okay, process-based models, and all those kind of things, trying to figure it out how to produce some crop yield forecast, okay, developing some methods. And most of that I'm showing here is basically examples from Florida, from the southeast, Florida, Alabama, and Georgia. And this is because I just moved in July, so I don't have enough information still on the Midwest. However, the last slide, well, not the last, but the last example I have is from Nebraska, and well, let's see what we're starting to do some research on that. Okay, first of all, we have the problem of the spatial resolution. Okay, here we have the Florida, okay, and these red points are the weather stations that we have there, and we can say, we can extrapolate, this depending on the topography, many meters or miles away from the weather station position. In the next point, we have again Florida, and this is a monthly amount of precipitation for a given year, doesn't matter, okay. And this is taken from radar. Okay, we have several radar data information here for 31 days or 30 days. And it's a very nice map because we have a resolution of 0.5 kilometers, right? So then what I started is to aggregate these small pixels, these small grids of 0.5 kilometers. So I took 20 by 20, okay, and aggregated, okay, I added, and basically I produced this map. Okay, this is every grid cell is 10 by 10 kilometers now. So we can see that we lose a little of information, but it's still there. We lose the keys, okay? If you want, like diving, okay, we don't have any of the keys. But anyway, I continue aggregating to the 20 kilometers, and this is most of the actual resolution of the regional climate models, okay? So, and you can see now that we can see the squares here, the cells, right? And definitely we started to lose a lot of information compared to here. I continue aggregating, so this is the level of regional circulation models. I continue aggregating to 100 kilometers, again, this is exactly the same information. And next I went to the 400 by 400 kilometers, okay? And this is the scale of a global numerical climate model, okay? In other words, this one is exactly the same like this one, okay? So this is how we see Florida in a global model, okay? So yeah, I guess we lose something, right? Anyway, so this is one of the problems, aggregation, okay? And for example, we know that the climate models tend to overestimate the precipitation, okay, the number of rainy days. And this is because in one cell, in one of these 400 by 400 kilometer cells, okay, we have like, I don't know, 200 weather stations. If at least one is raining every day, you have one. So that's why the models overestimate. And this is a problem of scale, basically, spatial scale. It's aggregation. Among others, parameterization of the models and this kind of stuff. This is part of the reason. Here we have a matrix where we have time, the X, and we have space, okay, in Y, and we have from 1 by 1 square meters up to the 400 by 400 square meters, okay. And in time we have climate, or in the past. This is the today line, okay. And we have future. We have seasonal climate forecast and climate climate change. So basically, this is all the type of information we have. We have the weatherization network. Okay, it's very in the past, maybe 100 years old. Okay, very dense. But the problem is that we only have the information till today, right? We have radar data that give us a much better flavor about the spatial distribution of rainfall, for example, compared to the weatherization network. However, again, is till today, it's observed data, and we can't go farther than, I don't know, it's the 80s or something like that. Okay, we don't have a long story. On the other hand, we have the climate models, okay, and in the climate models, they produce data from the past. Okay, let's see, they make a hindcast, okay, but the best they do is the forecast. And here we are talking about forecast in the case of seasonal climate, but also we are talking about climate projections, right? And again, we can go from GCMs, for the scale of GCMs, using dynamic downscaling, to regional climate models to, increase the predictability, to move again from this low resolution to this almost better resolution for 20 by 20 kilometers and so on. One important thing as we have this information is that called reanalysis. Okay, reanalysis is a kind of observed data, but this is at the grid scale. Okay, so what they do is they take information every 6 hours. Okay, from the past. Okay, they began in January 1st, 1949, I guess, depending on the reanalysis. And they took all the information, okay, from the atmosphere, satellites, weather stations, everything that's available, okay, and they make a forecast of 6 hours, okay. But again, we are in the year 49, right, and we know what happened. So we started to make the corrections, okay, and to the outputs. But what is important is that we go from this point base, okay, airplanes, boats, buoys, etc., to a global scale. So these models are used to fill all the missing values, okay, in all the points in space, okay, in the ocean, and in all the air. Okay, this is like observed data. It's model data, but this is like observed, like the standard data using the global. But again, the problem is that we have only till today. Every day, every 6 hours they are updating and we have this analysis. Then, for operational level, for crop and environmental modeling, okay, what we need is high resolution, okay, in space, but in the future, okay. And this is where we are working now, trying to improve the predictability skills and the resolution of the climate information to feed crop models, environmental models, and hydrological models, etc., etc. So all this process, this aggregation, these models produce a lot of uncertainty for the result we want to have. This is what we have in the global regional circulation models. Well, this is global and regional circulation models. And basically you have the observed data that could be reanalysis that I already explained, or for example 1981 till 2010, or doesn't matter, 2012. And we have on parallel the global models and the regional circulation models that basically produce this information. Okay, this is the hindcast, or also called retrospective forecast. Okay, plus the future. Okay, so what is the projection or the forecast for the next 3-6 months? Okay, what is important is that we have this information in parallel. Okay, so this is the kind of observed data plus the simulated. This is a real forecast. Okay, but again, it's made with information of the past. Okay, so it's a real forecast, but just retrospective. But basically, we can use this part of the story, okay, observed data and the GCMs, in order to measure the skills, okay, how good or how bad are the global and the regional circulation models. That's why we measure the skills. Now, I'm sure you have heard about this bias correction of the global models. They tend to overestimate or underestimate given variables. And this is exactly what I'm showing here. This is for rainfall, these two. This is for incoming solar radiation, and this is for maximum and minimum temperatures. Okay, different statistical distributions for each variable. The easiest for me is this one. Okay, the Gaussian distribution. We have the bell, no, and this is specifically for one county. But what we have here is these whisker plots represent 20 ensemble members, 20 realization of a regional circulation model. Okay, and this is a real forecast. Okay, so well, in this case, it's a real hindcast, right? And you have the variability, you know, and the variability change in terms of the month, and these black points are the observed data, okay, in a weather station here in county. Okay, so basically you have here, for example, in March, this is the real data, the observed data in the weather station, and this is plot here, a whisker plot, is showing the variability of the 20 ensemble members of the real prediction. Okay, so this is what we call bias. Okay, this figure here is the mean. Okay, so it's the mean temperatures. Okay, in March, and this is the hindcast, and so on for every month. Okay? But also we have the deltas, the bias correction, not only in the mean but also in the standard deviation. Okay, we are hearing more and more than in the case of climate change projections. We're talking about changes in the extreme events, right? So it's not only the mean but also changes in the variance. So we need to make corrections on this. So basically, what I already said, we calculate the deltas. Deltas are just the difference. Okay. So we have an observed period, for example, 81 to 2010, of this mean and standard deviation from these variables. Okay, and again, this is in a map, a kind of map of Florida, right? Our three grid cells, and we have the same information for the same period of time, 81 to 2000, the same variables, okay, the same time step, and we have the map of Florida with these projections of forecast. So basically, what we are doing is here is this maximum temperature of 20, and this is maximum temperature of 18. Basically, what we are doing is less, and this pixel will be 2, right? And so on for each pixel. So basically, we have a map of delta values, and the same will happen for the variability, for the standard deviation. Okay. The issue that I already mentioned is that for every grid cell, there are many weather stations inside. Okay, so when we move from this high-resolution precipitation map, okay, to these only 3 cells, okay, the difference is basically given by these weather stations that are inside. Okay, so when we make the correction, in this case, is we must use it for each. So all this area have only one delta value, and they will be applied for each one of the weather stations. Okay? This is how it works. Then you can complicate things, you can make interpolations, etc. But basically, it's the base. Okay. This is in another way. We have the original distribution, this red one. Okay, and every new observation, every daily observation, is equal to an old observation plus the delta. In our case, in our example, the delta was negative, so we are displacing this distribution to the left. Okay, so for every value here, we are decreasing the delta, and from this given time series, we have a new time series, okay, that is bias corrected. Okay? And exactly the same methods apply for climate projections, okay, because they said temperatures will increase in 1 degree, okay. So what we do to generate this new time series is basically do the same. We have our time series, and we can increase 1 degree, or we can, for example, multiply by 20% of precipitation, increasing or decreasing, and so on. Okay, so it's exactly the same method for the bias correction. The pros and the cons basically is the easiest to implement. It's just plus or multiply if we are talking about fraction of precipitation. Familiarity is the way climate change has been expressed. I already mentioned temperatures will increase, or precipitation will decrease in 20%, for example. It takes into account the spatial coherence of the data because are based on the global models, right? And the global models have all the physics inside that maintain, the relationship between temperatures and precipitation and winds and etc. And also it takes into account the static covariance among variables. This relationship of for example, precipitation and temperature. But I make emphasis that we are talking about a static covariance, okay? Because we are basically adding 1 degree, for example, okay, to a given time series. But adding 1 degree, okay, the correlation as a value, okay, as a statistics, is exactly the same. It's exactly the same. But the real relationship, and this is here the other point, do not take into account the ocean and atmospheric physics, okay? So, because now we have more temperature, for example, than precipitation, we are breaking this relationship that was built by the global models or the regional circulation models. So we spend a huge amount of time and millions of dollars running the models, and at the end, at the time we made the correction for the models, we mess up everything. And you will see the effects of that. Basically, provides a minimum measure of uncertainty, because if you have 30 years of data, you make your bias correction, and you have only one time series of 30 years, that's all. And the big issue here is that changes cannot be applied to the variability. Because basically we are moving on it, and we are saying, okay, we have changes also in the variability. We have bias correction also in the variability. There are some more complicated methods. For example, is the bias correction based on cumulative probability distributions. Don't worry, it's just showing, trying to impress you. Okay, and this is the case of precipitation, because precipitation is more complicated because we have two variables really in precipitation. The first one is frequency, okay, number of rainy days in a year, okay, and the second one is the amount, how much rainfall we will have, okay, in a given day or in a given month, okay. So these are more complicated, but basically what we are doing is again moving statistical distributions from one side to the other, okay. We have bootstrapping, or it's another method, it's another statistical non-scaling method. Basically, it's a resampling. We have the time series, okay? And the new values are exactly the same as the old values. The only issue is that we are sampling given a function, okay? For example, we take from our time series 3 days here, 4 days here, 1 week here, and so on, and we rebuild that one in a new time series. So it's real data, okay? By the structure in time, it's not, okay? But we are taking into account this delta value that we measured at the beginning. There are two methods, basically truncation. We want to increase the mean. We said, okay, we won't sample this part of the distribution. However, we are saying, okay, we won't have this part of extreme events in this area, right? And the other one is basically based on the sample, so we reshape the distribution, but the same remains. The new value, the new mean, will be the old mean plus the delta. Okay? We have now other type of methods, is point weather generators, and this is more stochastic downscaling more than statistical downscaling. And why we call it stochastic is because we are taking into account random numbers. Okay? And what we do is basically resample from a given distribution, and that's all. And again, we change the distribution, okay, by just adding the delta. This is very simple. Now, there's an advantage. Remember this figure I showed? It's not the bias is not only in the mean, but it's also in the standard deviation. Okay, and by now all the methods I showed before was only in the mean. Okay, so in this case, for the weather generators, we also can modify, okay, the distribution. No, before it was only from here to here the variance, but now we can change the shape, okay, and we can increase more, in this case, higher values, okay, for temperature. No? So we can, now we show that we are modifying also, not only the mean, but also the variance. Okay, so we use here the deltas from the mean and the deltas from the variance. Okay, so now we can include both of them. Okay. Basically, we take 1 point, we make the parameterization, we run the weather generator, and because it's a random process, okay, basically we don't make only one simulation, okay, of 30 years, as we said before, but now we have the capability of produce many, hundreds, one time series, okay, of data, and all of them are equally probable. Okay, so now we can measure exactly what is the uncertainty of using these type of methods in the downscaling. Okay, so it's not only the uncertainty of the climate models, but it's also the methods we are using to obtain the perfect information. And a little more complicated is when we have not only one weather station at a time, but we will have several weather stations at a time. In this case, for example, we have 3 weather stations, basically. And this is a black box, okay? It's the model, don't worry. And but basically, what is important here, again, each weather station, okay, each distribution will have the new mean will be the old mean plus the delta of this weather station A, and the variability too. Okay, so we have the same for B and the same for C. And remember, this weather station can be in the same grid cell, okay, or in different grid cells. But this black box, okay, maintains this coherence between variables and in space and time. And when this is important, imagine, for example, we have a watershed and we are making a study of soil erosion. Okay, so if we use independent downscale data, okay, we have, for example, 10 weather stations. Okay, and we started to analyze because they are estimated downscaled independently. We will have that at least 2 or 3 will be raining at the same time, and never, ever, ever that 10 at the same time. And this type of events, is raining everywhere, and all the watersheds at the same time are the ones who produce, the floods, the soil erosion. Okay, so this is another important part to have this spatial coherence. What it means now in terms of agriculture. Okay, we have done a lot of research on developing these methodologies. Kind of complicated, but but what is the effect in the crop models? In this case, we have the blue line, this one. Okay, this is the observed data, real data measured in the weather station. Okay, and the other 3 or 4 are different global models. Okay, CCSM3, GFDL, Harvey Center, and the PCM. Okay. In the left, these 2 belong to one county in Florida. Doesn't matter the name, really. And the other one is in Georgia. It really doesn't matter that much. And in the top, we have one scenario, emission scenario. This is the lowest one, A1B. And in the low, we have the A1FI. This is the extreme. And I guess now we are here, right? This is the real what is happening now. Anyway, and this is probability of accidents. I'll already explain this probability of accidents, how they work. Basically, in this case, we are taking number of days per year with minimum temperatures of 28 Fahrenheit. So this is important threshold for citrus, for example, in Florida. Okay, then because we can have the trees killed. It's not only you lose the harvest, but you can kill the tree. Okay, so we have, for example, in this green value, we have the 50% probability of exceeding how many? 22 days, okay, with temperatures lower than 28. This is how you read this one. But what is important here is that the comparison, okay? After all the bias correction, after all the downscaling, we usually see the statistics they show us, the climatologists show us, and that is perfect downscaling that fit the climatology, the monthly values of precipitation, etc., etc. But in terms of agriculture, it's different, okay, because there are different focus. So it's not only important that the climatology as a statistics, but the effects on the crops, okay? In this case, we have a very nice, this is the observed data, and these other 3 models fit pretty nice. This one, not at all, okay? In this case, the probability of having, for example, 15 days with lower than 28 Fahrenheit, okay, this is how much? 50%. But this model is giving me the probability of, I don't know, 80%, 85%. Okay, so it's that over forecasting, over projecting, I don't know, the number of events with the number of days with this lower temperature. Okay, so we can trust that model. However, in the next one, okay, it makes a nice, well, not nice, but still similar to the other models. Okay, so we can see that this is location. It's important where we are. Okay, we can trust one variable or not, and also the model, the scenario. Okay, how the model is configured in the simulation. And we have here again the red one CCSM3, okay, you can't trust this one in this scenario. And here's another variable. This is cumulative growing degrees using 60 Fahrenheit threshold. This is from May 1 to September 1. This is usually the cropping season for that area. And we already saw, Ken show some example with using 50 Fahrenheit as a threshold for the cumulative degrees. And again, same scenarios, same cumulative coincidence. And you know, this is a very nice performance of the models. Okay, and again, this is a very important measure that is used by the crop models to simulate crop growth and crop development. You know? Again, some problems here of underestimating probabilities. Very nice job here, and here there is some problems. Another variable, this is not so good, right? We have the number of dry periods, okay, lasting more than 10 days for 3 months centered on April. Don't worry for the second line. Number of dry periods lasting in more than 10 days during the cropping season. Okay? This is the real data, the blue one, and these are the models. Huge problem, right? And you know, they are just underestimating these periods of, you know, these dry spells that can affect the crop. Okay, and what is the consequences of that? Is this one. This is ensemble members. This is in the top. We have observed data, we observe weather, real weather. Okay, and these other 20 lines here, okay, are a regional climate forecast. Okay, hindcast. Sorry. But what we're showing here in this part of the figure is the period of water stress affecting growth. Okay, basically stress. These thick dark are water stress, and the other is unstressed period. Okay, so we can see exactly when the water stress affected the graph. In the second column, part of the graph, we have yields. Okay, and everything is simulated. Remember, using crop models. And the last one is rainfall. Okay, this is the total amount of rainfall during this cropping season of 130 days. And this is, you know, split by month. Interesting here is that we got the ensemble number 2, the highest amount of precipitation, of total precipitation for the cropping season. Okay? But when we see the yields, we have one of the lowest yields compared to the other ones. In ensemble number 6, it's totally the opposite. We have one of the lowest amount of precipitation, however, one of the highest amount of yield. Okay, I mean, if you try to work in what they taught me at the university, you know, higher precipitation, higher yields. Okay, this just break all the schemes. But what happened is that this is only 1 year. We analyze exactly when, you know, for the higher precipitation event ensemble, this dry spell occurs. Okay. It was exactly during tassoning, during flowering. Okay? And this event, this problem, the timing when this stress occurs, affect, you know, the productivity of the yields. Okay? So, going back to this figure, having this problem with these periods lasting, you know, a bad forecast or a bad projection, okay, from this type of dry spells, it really affects our projections, okay, not only in seasonal climate for the next season, but also for climate change. There's another one, this is the last one, is total precipitation for April, planting date. And again, some, this is observed, some models are doing a very nice job, but others just doesn't work. Okay, so we need to be very picky. Okay, we need to know exactly. We need to do this type of evaluation before taking just an output for whatever model and just making a projection. And this is one more. And this is again same models. The black is the observed data, and this in this case is using crop models. This is for Mitchell County. This is the hindcast 61 to 2012. Yes. And this is rainfall conditions, and this is optimal irrigation. Okay. We can see this is what really happened. This is 2 models, you know, and these are the other 2, and basically there is nothing there in predictability. There is nothing. If we go to irrigate it, there are two parts of the story here. This part is really nice, right? Because we are irrigating, we are removing the problem of the forecasting, the level of skill of predicting precipitation. However, we have this part of the curve, okay, that tell us that we have all the time we have 10% or 15% of zero, so total crop failure. Okay, what in fact we never have a crop failure. Okay, so the model in this case are having problems. That the climate information is having problems in representing the low temperatures, because we have over predicting, the low temperatures and the freeze events at the end of the beginning or the end of the cropping season. Okay, so again we have this problem if we want to go forward, for example, for extrapolating this data for what will happen in 2030, 50, or at the end of the century. Okay, these are the things we need to take into account. And this is for Nebraska. This is one of the last slides. And this is just did this research. This was the effect of ENSO on crop yields in Nebraska. I'm using these statistics, this time period of time. Okay, and I use statistics from NAS. Okay, we have wheat, irrigated, not irrigated, soybean, and potato. In potato, there is no differentiation between irrigated and not irrigated. And we have, this is La Niña in blue, neutral years, and El Niño. Sorry, here I put La Niña is El Niño. My mother is a teacher in the school. She will kill me if she's seeing this. So please delete that and not be the tape. Okay? Anyway, so what we're showing here is the percentage, okay, of increasing or decreasing in productivity due to ENSO. And this is exactly what Al showed in his presentation. Remember that what is the effect of El Niño during El Niño, cold events, warm events, all these changes in the jet stream, okay, and the water circulation, and so on and so on. So here is the application of that information they predicted. Okay, so we can see, for example, that if we compare irrigated versus rainfed, of course, irrigated, we also defend ourselves, okay, the problems of drought, right? But but still there is a signal, right? We decrease in 3% during La Niña event and 2.8 more than normal, okay, during El Niño. And in wheat, during the rainfall conditions, La Niña decreased 9%, and we can increase on the average 5% during the Niño events, and so on. Okay, so we can take advantage of this climate science, okay, in order to make predictions. And we have the same for different crops. However, there is a trick here, okay? And it's exactly the same that what I was talking about before about the climate change models, okay? This is not all the story. What I took here is the rainfall data for every year, okay? This is the yield residuals, okay? Basically, the value less the mean. And by the way, I already removed technological detraining. I made the technological detraining here, okay? So basically, if you analyze here, you can see most of this is with rainfall here, most of the red points, El Niño, okay, are positive, okay? So corresponds to this increase in 4.6%. And most of the blue points are in the bottom part, right? You can see. And this is corresponding to the negative, almost 9% of increase in the average. And okay, the neutral values are almost in the line. However, when we try to communicate this information to the farmers, okay, we cannot give them only this information, okay? Because if you see here, during La Niña, okay, is less than 9%, okay? However, we have, for example, these 2 years, 2 Niño events, okay, that are almost, negative 7–8%, okay? So this is part of the variability. Okay, so when we talk with the farmers, we need to transfer not only these deterministic values, change in production, but also the variability. And this is why we always talk about with probabilities, and never in deterministic ways. In the same we have to do with climate change projections, always as a probability, and show this type of information that not always you will have this. It will be very nice, but there's a variability inherent in this one due to the climate variability that will affect these results. Okay, And when you transmit this information of using climate information to farmers or users in general, you have to take into account this information. It's very important because you can lose, the trust you can have. Okay. As a conclusion, I love X-Files. So trust no one, right? Well, it's not complete, right? Really, it's trust not one who doesn't show you. Okay. Model validation. What is the model? How the model works? How the results are? Okay. In what variables? Okay. And number two, the measures of uncertainty. Okay. As a probability values, not as a deterministic ones. And always, and this is very important and very new, especially for the climatologists. Okay. In terms of the specific applications, as I showed you before. Okay. If we show the statistics of this, or applying all these downscaling methods, it just fit perfect. The total precipitation and the mean temperatures and so on and so on. It's just so beautiful, it's unbelievable. Okay? I've done that work myself. And I was ready to get my Nobel Prize when I started to apply this information to the crop models with the daily variability. And I almost killed myself. It was crazy. It was no predictability at all. No? So we need to find why they are not working. This is why I show you this problem with the stress. Okay, and the timing with dazzling, this is very important for the forecasting. So this is important in terms of the specific application. If you are doing hydrology, okay, show me the forecast, the hindcast, okay, and the validation and the measures of uncertainty based on, I don't know, soil erosion, for example. This is what then you can extrapolate to the future for the next season or for the next 30, 100 years or whatever, okay? So this idea, and this is the message why we need to take, these two things into account. So my name is Guillermo Baigorria, this is my email, and if you need to contact me, there you are. Thank you very much.